So welcome back to my lectures on Galois theory. Our next topic is some illustrations of Galois theory. In this session, what we are going to do is we are going to study the symmetric functions. The symmetric functions, let us take an example. Let us take an example f of x. You have two variables x comma y. This is a function in two variables x and y. Let's take this as 3x squared plus y. So what we do is swap x and y. Replace x with y and y with x. So what happens? F of yx is equal to 3y squared plus x. We know that f of xy is not equal to f of yx in this case. But if you take another example, f of xy is equal to x plus y plus xy. So if you swap this, f of yx is equal to y plus x plus yx. In this case, f of xy is equal to f of yx. So this is a general idea of defining a symmetric functions. Now we'll extend this one to n number of variables. So we'll consider a function f of y1 comma y2 dash 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 yn, n number of variables. If this is equal to f of these variables in some other order, probably y2, y1, then y3 dash dash yn. For any combination if you take of this y1, y2, yn, if you take any combination and if you evaluate that function, if they are equal, then we say f is a symmetric function. That is a basic idea, but we are not going to define a symmetric functions like this. We are going to involve field theory for the definition of this symmetric function. See how it goes. So our idea is to define a symmetric function using automorphisms. So let us consider a field. Let f y1 dash dash yn be the field of quotients on f of y1 dash dash yn. This is a ring and this is the field of quotients. So the general element of f of y1 dash dash y1 is going to be f of y1 dash dash yn by g of y1 dash dash yn where these two are polynomials and G is different from 0. So we are going to take only the symmetric polynomials, not any symmetric functions. So we want to define symmetric functions using automorphisms. So when do you say an element in this field is a symmetric function? F belongs to f of y1 dash dash yn is symmetric if f of y1 dash dash yn is equal to f of y sigma of 1 comma y sigma of 2 dash dash y sigma of n for all sigma in Sn. Sn is the symmetric group on n elements, all group of permutations. So we want to use this to define an automorphism to define the symmetric function. So our automorphism is going to be like this. See, this is f of y1 dash dash yn, and saying there are several automorphisms on here, but we are going to consider only very specific automorphisms. That automorphisms are induced by the permutations. So for sigma in Sn, define sigma bar from f of yn dash dash yn to f of y1 dash dash yn by sigma bar of f of y1 dash dash yn is equal to f of y of sigma of 1 dash dash sigma of n. This is a valid function. What we are going to do is replace 1 with the image of sigma. So if this is if some in a particular case, probably y1 will point to y3, yn will be pointing to y7, something like that. So what we will do is here we'll say sigma bar belongs to Sn of this. This is the collection of automorphisms from f of y1 dash dash fn to f of y1 dash dash sn, where sigma bar is defined like this. If you define like this, then what are the symmetric functions then? Then if f of y1 dash dash y, sorry, instead of doing like that, if sigma of f, sigma bar of f is equal to f for all sigma bar in Sn, then f is symmetric. Right? So we will write it in another different way, is equal to f belongs to f of y1 dash dash yn such that sigma bar of f is equal to f for all sigma bar in Sn. So what is this? This is actually the fixed field of Sn bar, meaning how do you write it? F of y1 dash dash yn, then you have a Sn here, Sn bar. Sn bars are automorphisms on f of y1 dash dash yn defined like this. So that is how we are going to define the symmetric functions. So from now on, the symmetric functions will be defined like this, not in terms of the quality of the values of members from here. So the definition goes like this. An element f y1 dash dash yn in f of y1 dash dash yn is symmetric if it is left fixed by any permutation or all permutations left fixed by all permutations on y1 dash dash yn, or we'll define in another way, if sigma belongs to Sn, define automorphism on f of y1 dash dash yn such that define automorphism sigma bar. Sigma bar of f of y1 dash dash yn is equal to f of y sigma of 1 comma y sigma of 2 dash dash y sigma of n. Then the elements of the fixed field of Sn bar over f of y1 dash dash yn is a symmetric function. Where Sn or sigma on the automorphisms, sigma is an automorphism on f of y1 dash dash yn defined by sigma bar of f of y1 dash dash yn is equal to f of y sigma of 1 dash dash y sigma of n, where sigma belongs to S. So that is the definition of a symmetric function or symmetric polynomial using automorphisms. So we know that the collection of all symmetric functions on the collection of all symmetric functions on f of y1 dash dash y1 yn is a subfield of f of y1 dash dash yn. And in fact, this is the fixed field of a collection of automorphisms, and that automorphisms are generated from the permutations on y1 dash dash yn. Now, we are going to define some elementary symmetric functions. Elementary symmetric functions. So we'll start from a very simple one. It's called S1 y1 plus y1 plus y2 plus dash dash yn. Definitely this belongs to f of y1 plus dash dash, and it is symmetric because if you permute between the numbers from 1 to n, it remains same. So this is the first symmetric function, and this is the first elementary symmetric function. So you can define another symmetric function of order 2, of degree 2. This is degree 1. Degree 1 of on y1 dash dash yn. So this degree 2 will be y1 y2 plus y2 y3 plus dash dash plus yn minus 1 yn. Like that, you can define Sn is equal to y1 yn y2 dash dash yn. So these are actually, if you consider a polynomial f of x is equal to pi I is equal to 1 to n x minus yi. This is actually an element in f of y1 dash dash yn. This is the field and this is the polynomial. So these are actually, if you expand this polynomial, these will be the coefficients of x to the power of n minus 1, x to the power of n minus 2 dash 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 x, the constant term. Well, without any sign. See, the coefficient of x to the power of n minus 1 will be minus of 1 plus y2 dash dash yn. Actually, that is equal to minus s1. So this is actually going to be x to the power of n minus s1 x to the power of n minus 1 plus s2 x minus n minus 2 plus dash dash dash. our objective is the collection of all symmetric functions. That is that is actually the field of all symmetric functions is equal to the field of S1 comma S2 dash dash Sn. These are also symmetric functions, but we are considering a field on S1, S2 and S3 and Sn, not on Y1. So our objective is the field of symmetric function is equal to this. So that is what we are going to prove. So before we start proving the main result, we need to prove one result from splitting field. Let f of x is a polynomial in f of x and E be the splitting field of f of x over f. Then the degree of E over f divides n factorial, where n is the degree of f of x, and that implies the degree is less than or equal to n factorial. So for every f of x in f of x, there exists a splitting field. Right? We will prove this by induction. Assume that n is equal to 1, which implies f of x is linear, and which implies E is equal to f, and which implies E of f is equal to 1, and that divides 1 factorial. So for n is equal to 1, the result is trivial. And assume now the result is true for all for n and less. And we'll prove that the result is true for n plus 1. So let f be a polynomial in f of x of degree n plus 1. And let alpha be a 0 of f of x with degree is equal to p, which is greater than 0. Or you can say degree of alpha over f is equal to p. If it is 1, then f is irreducible. So we'll assume that p is greater than 0. So this implies f is a subfield of f of alpha, which is a subfield of E. Right? Now, what we will do is so this actually this implies f of alpha is the splitting field of f or of irreducible polynomial of alpha over f. What I'm trying to say here is our f is equal to, let us say our f is equal to x to the power of 4 minus 5x squared plus 6. Then this is the zeros are root 2 minus root 2, root 3 minus root 3. Our alpha is equal to root 2. So the irreducible polynomial of alpha over f is equal to x squared minus 2. That's what this one is. Now let q of x is equal to f of x by the irreducible polynomial of alpha over f. So this means the degree of q of x is equal to n plus 1 minus p. So here the q of x is equal to x square minus . So what happens here? This implies, so what is happening here is, this is our q, and the splitting field of this one is q of root 2 comma root 3, and we have root 2 as an alpha, so this is q of root 2, and root 3 goes outside this q of root 3, root 2, so this is somewhere here. So we can consider E, so E is the splitting field of q of x over f of alpha. So that means, see here f of alpha is a splitting field of f of irreducible polynomial, and this is also a splitting field. So both of them are less than n plus 1. So what does this mean? This means that E over f of alpha divides n plus 1 minus p factorial and f of alpha column f divides p factorial. But we know that E over f is equal to E over f of alpha times f of alpha over f. This divides, so this implies divides n plus 1 minus p times p factor. And that implies n plus 1 minus p plus p factor. See, if a factorial times b factorial divides a plus b factorial. So that means, so this implies, I'm going to write it here, the degree of E of divides n plus 1 minus p plus p, that is actually n plus 1. And that is the proof of this. Now we'll come to the main proof. So let us assume that K is equal to the field of all symmetric functions in f of y1 dash dash yn, and E is equal to f of s1 comma dash one sn, where sn's are or si's are elementary symmetric functions. So, what are Sns? S1 is y1 plus y2 plus dash dash yn, and S2 are y1 y2 plus y2 y3 plus dash dash y and minus 1 yn. Sn is equal to y1 y2 y3 dash dash. So these are all symmetric functions, and f is the field of quotients of polynomials on these. So every element in this field is a symmetric function, which means that clearly E is a subfield of K, and which is a subfield of y1 dash dash yn. Now let us consider a polynomial f of x equal to pi I is equal to 1 to n x minus yi. The coefficients of this polynomial are in E, so definitely it belongs to E of x. And zeros of these polynomial are y1 dash dash yn, and therefore f of y1 dash dash yn is the splitting field of f of x, which implies from the previous result the index the degree of f of y1 dash dash yn over f over e is less than or equal to n factorial from the previous result. Now, what is the index of f of y1 dash dash yn colon k? K is the fixed field of a subcollection of automorphisms on f. What is that subcollection? That subcollection is Sn bar, which corresponds to the permutation in Sn. So, the order of that group is n factorial. But this has got more automorphism than just this. So, this is actually greater than n factorial. And this is always less than or equal to the degree for every finite extension. And E is a subfield of K. So this actually implies the degree of f dash dash yn over K is less than or equal to the degree of f of y1 dash dash n over E. So this is actually less than or equal to f of y1 dash dash yn colon E, and which is less than or equal to n factorial. So we started with n factorial and ends with n factorial, which means that these two are equal. This implies f of y1 dash dash yn or k is equal to f of y1 dash dash yn or E, and that implies k is equal to, and that is a proof of. Let us do one problem using this result. Express the symmetric function y1 by y2 plus y2 by y3 plus y3 by y1 plus y1 by y3 plus y2 by y1 plus y3 by y2 in terms of S1, S2 and S3. What does the theorem say? The theorem says this is a symmetric function. So any element in the symmetric functions can be expressed in terms of elementary symmetric functions. S1 is equal to y1 plus y2 plus y3. Of course, these are all in f of, these are all in f of y1 comma y2 comma y3. Okay, so S1 is this, S2 is equal to y1 y2 plus y2 y3 plus y3 y1. S3 is y1 y2 y3. So let us compute this. Y1 by y2 plus y2 by y3 plus y3 by y1 plus y1 by y3 plus y2 by y1 plus y3 by y2. So that is equal to y1, y2, y3. When you compute this one, this will be y1 square y3 plus y2 square y1 plus this one is y3 square y2 plus this one will be y1 square y2 plus this one will be y2 square y3 plus this one will be y1 y3 square. So this is definitely S3. So we need to express this one in terms of this combination. So what we will do is, we will multiply S1 and S2. S1, so let us say this is actually equal to probably f of y1 comma y2 comma y3 by y1 y2 by S3. We are taking this one as y1 y2 y3. So S1 times S2 is equal to y1 plus y2 plus y3 times y1 y2 plus y2 y3 plus y3 y1. So this is actually equal to, if you expand this one, y1 square y2 etc. That is going to be f of y1 y2 y3. If you expand this one, you are going to get this whole thing. So this is going to be equal to S1, S2, sorry, there is, when you expand this one, there is something else here going on. So if you expand this one, y1 square y2 plus y1 y2 y3 plus y3 y1 square plus y1 y2 square plus y2 square y3 plus y1 y2 y3 plus y1 y2 y3 plus y2 y3 square plus y3 square y1, and that is equal to f of y1 comma y2 comma y3 minus or is plus 3 S3, because this is an S3, this is an S3, this is an S3. All others, if you compute, it's going to be the whole thing. So this will be so f of y1 y2 y3 is s1 s2 minus 3s3, s1 s2 minus 3s3 by s3. So that is how we express this symmetric function in terms of elementary symmetric function.